Hello, Math 1090 class. Today I'd like to start talking about Chapter 6.1, Simple and Compound Interest. In this chapter, we will explore two forms of interest, simple interest and compound interest. However, this discussion must first start with principal, or the amount your account starts with. This could be a starting investment or the starting amount of a loan. Interest, in its most simple form, is calculated as a percent of your starting principal. For example, if you borrowed $100 from a friend and agreed to repay with 5% interest, then the amount of interest you would pay would be 5% of the $100. Which is 100 times 0.05, always write your percent as a decimal, which comes out to be $5. The total amount you would repay would then be $105, the original principal plus the interest. If this makes sense, let's start investigating this idea a little further. First, let's look at some definitions. Simple one-time interest is interest that is paid on an investment or loan at the end of the loan period, and it is calculated as a percent of the starting principal or your starting balance. So from our previous example, the interest is going to be your principal times your interest rate times the time that you have the loan out for. Your ending balance, A, is going to be your original principal you started with plus the interest that you calculated from your previous line. Notice that this equation is in agreement with how we started our previous example from borrowing $100 from a friend. However, instead of writing I for interest, let's replace I with what we said it was, PRT. In which case, now we have two terms that have a common factor of P, and we can factor P out and write a more simple formula that tells us the amount that an account will have at the end of the period. Now, in this formula, A is going to be the end amount, which is the principal plus the interest. P is the principal, or your starting amount. R, your interest rate, always written as a decimal. And T will have to be your time in years. Another definition. Here, APR refers to annual percentage rate. And this is the total interest that will be paid in the year. If interest is paid in smaller increments, the APR will have to be divided up. And I'll show you that in some examples. Another type of interest that we'll calculate is referred to as compound interest. Compound interest is added to the balance, added to the balance of the account at the end of each compounding period. And then future interest is calculated on this accumulated sum. Your formula for compound interest, a little bit more complicated, will give you your ending balance, A. It's going to be your initial principal, P, times 1 plus your interest rate, R, written in a decimal form, divided by K, which is the number of compounding periods in 1 year, raised to the exponent kt. Now you might recognize this formula. This is the same formula we presented in chapter 5.1. We will explore this formula in more depth now that we are in chapter 6.1. Let us look at an example. Suppose you lend a friend $500. that they agree to pay back at the end of the year with 5% simple interest. Now notice this is very important that they do tell us simple interest. How much interest will you earn? How much will you get back at the end of the period or the end of the year? So here I want to use the formula we developed earlier that said A, the balance of your account, is always going to be your principal P times 1 plus your interest rate times time. Here, our initial principal, our initial balance would have been $500 times 1 plus our interest rate, always written as a decimal. Take the 5%, remember to write it as a decimal, move your decimal point, which is currently at the end, 2 places to the left to get 0.05 times T, which would be the 1 year. And let's calculate this on our calculator. Make sure you follow along with me. Every calculator is different, and I want to make sure you're able to get these same values. So here we have the $500 times the 1 plus your interest rate, 0.05, times 1 for 1 year. Notice this gives us an ending balance of $525. So there are 2 parts to this question. One part was how much do you get back at the end of the year? And we'll say you will get $525 back at the end of the year. How much interest will you earn? Well, since we started with a balance or amount of $500 and we got back $525, we can say we will get back $25 in interest. Let's look at another example. Find the simple interest on a loan of $3,200 at 7.6% interest for 8 months. Let's start with our simple interest formula again. A equals P times 1 plus RT. Here our starting principal, $32,000. 1 plus our interest rate written as a decimal. Move your decimal point 2 places to the left. It'd be 0.076. Now here we're only in for 8 months, but in our formula T always has to represent time in years. So 8 months, to convert that to years, I'm going to divide by 12 to recognize that we have 8 months or 8/12 of a year. Now, a lot of times it might be simpler when you add this to your calculator to maybe, well, actually, we'll just enter in the calculator just like this. So here we go, 32,000 times the 1 plus 0.076 times time in years, which we said would be 8/12 of a year. Notice that I'll need 2 parentheses here, 1 parenthesis to close off the fraction 8/12, another parenthesis to close off the starting parenthesis I put here. This will give us an ending balance on our loan of $33,621, and since we're talking about money, it would make sense to round this to the nearest penny. Let's call this 33 cents. This would be your account balance at the end of the 8-month period. Let's try another example. A certificate of deposit A CD is a savings instrument that many banks offer. It usually gives a higher interest rate, but you cannot access your investment for a specified length of time. Suppose you deposit $3,000 in a CD that pays 6% interest compounded monthly. How much will you have in the account after 20 years? Now, in this problem, they do tell us that we're compounding monthly. This would be in comparison to the previous examples where they're telling us that we were doing a simple interest. So look for these words in the question to make sure you grab the right formula. Now, on this CD example, since we are talking about compound interest, let's grab our compound interest formula. Here, our compound interest formula, A is going to equal your starting principal, 1 plus your interest rate divided by the number of times you compound interest per year, raised the KT. Here we started with an initial principal of $3,000. 1 plus your interest rate, always written as a decimal, divided by the number of times we compound interest per year. Here we're compounding monthly, so we're going to let K equal 12. Raised to the 12 times time, which we're investing our money for 20 years. So 3,000, starting parenthesis, 1 plus 0.06 divided by 12, raised to the, now you might again have to put parentheses on your exponent depending on how calculator works to make sure that the product 12 times 20 stays as an exponent. My calculator clearly does put it as an exponent, so I'm not going to need parentheses here. And I calculate that we have a balance after 30 years of $9,930. And again, since we're talking about money, let's round this to the nearest penny. 61 cents. This would be the amount of your CD after 20 years when interest is compounded monthly. To investigate this idea a little further, let's suppose you deposit $2,000 in an account earning 7.25% interest for 6 years, with interest that is compounded as follows. How much will you have in the account? Now, to save us a little bit of time, I started writing the formulas for us. Now, and I actually noticed I forgot to add the initial $2,000 in our formula. So actually all of these should have a $2,000 in front. There we go. Notice that when I'm changing the compounding period, I'm changing the value that appears in the denominator, how many times we're dividing our annual interest rate up, and that will always match the value of one of these factors in the exponent. Now, I'd like to make sure that you feel confident enter these in your calculator, so if you could pause the video for a moment, make sure that you feel confident entering these in your calculator, and then after you get a response, unpause the video and let's verify that we get the same answers. I hope you did that. Let's confirm our answers. For a $2,000 in deposit, earning interest at 7.25% for 6 years, when interest is compounded annually, I get a balance of $3,043.78 when I round to the nearest penny. When I compound the interest monthly, we're dividing our APR by 12. I get a balance of $3,085.88. When we compound our interest weekly, we're doing it 52 times a year. I get a balance of $3,088.99. When we compound our interest daily, we're taking our APR, dividing it by 365 compounded payments or compounded interest. This will give us a balance of $3,089.79. I hope you're able to duplicate these values. We should observe that increasing the number of compounding periods increases the amount of money that we earn. However, there is a limit to compounding. Notice that the increase from an annual to monthly compounding is larger than the increase from monthly to weekly or weekly to daily compoundings. What I'm asking you to notice here specifically is the increase that we see when we go from this compounding annually to compounding monthly seems to be quite large. It looks like it's around $42. I'm not calculating this from a calculator, I'm just approximating it. While when we go monthly to weekly, it looks like we have a gain of about $3. And while we go from weekly to daily, we have a gain of roughly $1. Now, normally you and I cannot walk into a bank and dictate which compounding periods we will receive, but this does go to show you that compounding more frequently does increase your end balance, but with diminishing returns. Most people, you and I, we live in a world where our interest will always be compounded monthly, which seems to be a nice medium with the different compounding periods that we can look at. Let's look at another example. Suppose you currently have $3,800 in an account that has an interest rate of 6.5% per year compounded semi-annually. Notice when we talk about semi-annually, we're talking about K interest being compounded twice a year. You want to be able to withdraw all your money when it reaches $9,500. How many years will it take until you're able to withdraw your money? Now let's get to the first part of the question first. We're talking about interest that's being compounded semi-annually. And so we know that our account balance A should be our initial investment, the $3,800, 1 plus our interest rate written as a decimal, divided by the number of times that we compound interest per year, semi-annually. We're doing it twice a year, raised to the 2t. Now we want to find out how many years it'll take until we get to 9,500. Specifically, we're being asked to find t such that the amount of our account, which we have as 3,800, 1 plus 0.065 divided by 2 raised to the 2t. We want to find out when this eventually equals 9,500. What this gives us is an equation where we want to solve for t. So let's proceed. To solve for t, let's first divide both sides by the 3,800. This will give us 1 plus 0.065 divided by 2 raised to the 2t. 9,500 divided by 3,800 on the right-hand side. If this were not a friendly number, I would leave this as just 9,500 over 3,800. However, since it's a nice friendly number, I don't have to do any decimal approximations. I'm going to go ahead and write the value 2.5. Now to solve for t, I'm going to use some of the properties, some of the methods we learned in Chapter 5. To get t out of the exponent, let's apply a natural log function to both sides. The natural log function, like any function, or any exponential function, has the property that it allows us to take exponents and move them as coefficients. So this will give us 2t times the natural log of the 1 plus 0.0625 divided by 2 equals the natural log of 2.5. Now a note here, one of the most common errors that I see students make is that they forget to write this natural log function. Make sure you apply the natural log to both sides and not just the left side. The natural log must appear on the right side as well. Now, to get t by itself, let's divide both sides by the portion that's not t. So I'm going to divide both sides by the 2 natural log of 1 plus 0.0625 divided by 2. This will tell us t should about be the natural log of 2.5 divided by 2 natural log 1 plus 0.0625 divided by 2. Let's calculate this on the calculator. So natural log of 2.5 divided by. Now, on this problem, when you're entering your calculator, you need to be specific about what the denominator of your fraction is going to be. You're going to have to put an extra set of parentheses here to make sure that all of this is in the denominator. So let's start off here with a pair of parentheses to specify the denominator. So it'll be 2 natural log. Notice it gives me another parenthesis for the 1 plus 0.0625 divided by 2. We'll have to put one parenthesis to close off this one where next to the 1, and another parenthesis to close off the denominator that we started here. And I get this to be 14 point, let's round this to 2 decimal places, 89 years. It'll take 14.89 years for our account to grow to $9,500. Let's move on. And talk about annual percentage yield. The annual percentage yield, APY, is the actual percent a quantity increases in 1 year's time. APY is commonly used to compare two different investment funds that have different terms. And I'm noticing right away when I wrote this out, I did spell two wrong. This should be two different investment funds. Now your formula for APY is given as 1 plus your interest rate divided by your number of compoundings raised to the number of compoundings minus 1. And as before, R is your annual percentage rate, your APR. K is the number of compounding periods in 1 year. Let's look at an example. Alexis has an investment account that earns 6.87% annual interest, compounded monthly, while Nina has an investment account that earns 6.14% annual interest, compounded quarterly. Compute the annual percentage rate, APY, that Alexis and Nina are receiving, and then determine which one of the two has a better investment option. So here we go. Let's calculate the APY for Alexis first. Alexis, her annual percentage yield, APY, is going to be 1 plus her interest rate as a decimal. So with the 6.87%, move your decimal 2 places to the left. This would be 0.0687 divided by her interest is being compounded monthly, so divided by 12, raised to the 12 minus 1. While Nina, her APY, or annual percentage yield, would be the 1 plus her interest rate as a decimal, which is the 6.14%, 0.0614, divided by her interest is being compounded quarterly. If it's being compounded quarterly, it's being done 4 times per year, so K is 4, raised to the 4 minus 1. And let's determine what this is on our calculator. Again, parentheses are going to be important here, so let's put our starting parenthesis, 1 plus 0.0687 divided by 12, parenthesis, raised to the exponent, 12 minus 1. Now make sure this minus 1 does not appear in the exponent. Your calculator might have put parentheses around this, but on mine, I just hit the arrow over button. Notice I'm no longer in the exponent, and I can do my minus 1. Remember, everybody's calculator is different, so make sure you're able to duplicate this in your calculator. You should get an APY of 0.0709 if I go to 4 decimal places. As a percent, this would be 7. Did I enter this correctly? Make sure I got this right. 1.0687 divided by 12 raised to the 12 minus 1. Yeah, that looks right. So this comes out to be 7.09%. It was just odd. In my notes, I wrote something different, so it made me question what I entered in my calculator. Let me just make sure I did enter that correctly. 1 plus 0.0687 divided by 12 raised to the 12 minus 1. Let's do the same thing. Let's calculate Nina's APY. So starting parenthesis, 1 plus 0.0614 divided by 4, since we're compounding interest quarterly, raised to the 4. We'll get our 1 out of the exponent, minus 1. Here I get a decimal version, 0.06. If I go to 4 decimal places, this would be a 2.8. And as a percent, this would be 6.28%. So while even though they have different compounding periods and different interests, comparing the two, we can say that it appears that Alexis has a better investment option. Now this completes all of the examples I have for you for chapter 6.1. This should give you everything that you'll need for your homework tonight. I hope this has been helpful, and I'll see you for the next video.